Hello everybody, welcome back to Total Organic Chemistry. This video is going to be a bit of review on resonance structures and how to draw them, as well as a discussion on molecular orbitals and hybrid orbitals. So resonance is a very important topic in organic chemistry, and it tells us a lot about the reactivity of many molecules in everything that we'll be studying in this sequence of videos. Resonance is a phenomenon where multiple structures of a molecule sort of combine and all contribute to an overall hybrid structure. So to show what I mean, we can draw the Lewis structure for the carbonate anion, so CO3 with a charge of 2-. If you're interested about learning how to draw Lewis dot structures or need a little bit of review, you can go see my last video on the review of bonding. So if we draw our Lewis dot structure, we'll find out that we have this sort of structure here. So we have one carbon-oxygen bond that's a double bond, and the other two are single bonds. So this is a good resonance structure. Don't forget our formal charges. Remember, we have a minus charge here for the one oxygen, and then a minus charge here again. They both own 7 electrons to themselves, and that adds up to our 2- charge there. But resonance is interesting because we can do certain things with this structure that we drew. We can actually take one of these pairs of electrons, move them down, and I'll talk more about arrow notation in a video to come. Let's erase these lone pairs here. I didn't mean to draw 3 pairs of lone pairs. Okay, so we can swing one of these pairs of electrons down to make a double bond between these atoms here, and then swing the double bond electrons up to make a lone pair on the oxygen. And what that gives us is this resonance hybrid, or resonance structure, excuse me. And our formal charges. So now we have a different structure, where the double bond is now between a different oxygen atom and the carbon, the central carbon. And we can of course do that again. Swing, excuse me, these electrons down. And for these resonance structures, I am using double-headed arrows to communicate that these are actually resonance structures and there's no defined chemical reaction happening. So we have 3 resonance structures. They each carry the double bond between a different oxygen atom and the central carbon. And resonance tells us that these structures are all equivalent. So these structures all kind of add together to equal this resonance hybrid here, where we have partial, let's make that a little bit better, partial double bond character between all of our oxygen atoms in the central carbon. And then we also have a partial negative charge on each oxygen atom. So this is our resonance hybrid. And this tells us how the molecule is, it tells us more of the truth of how the molecule is actually structured in real life. Because with resonance, it's sort of like mixing blue and yellow. These structures are not separate, and we can't differentiate between them. Resonance is a misleading term because that implies that these structures are resonating between each other, where they're very quickly oscillating back and forth, but that is not really the case. What is really occurring is that all three of these exist at the same time, and they exist in this hybrid structure that I've drawn here. So when we observe the carbonate anion, we see that all the bond lengths are the same, and all of the bond angles are the same. The bond lengths are the important thing because we know that double bonds are shorter than single bonds. So if we observed these separately, we would probably observe one bond to be shorter than the others. But the reality is that it's comprised into a single structure. And my analogy with blue and yellow is that if you mix blue and yellow food dye together, or blue and yellow paint, you don't see an oscillating mixture of blue and yellow. You see green. So it's very important to keep in mind that resonance structures contribute to an overall hybrid and not as very quickly oscillating different structures. And we will talk about resonance much more as these videos progress. There are three things to keep in mind when drawing resonance structures. One is to maintain as many octets as possible. So for example, if we have formaldehyde, we can draw this Lewis dot structure to begin with, which is our best Lewis dot structure. It's how we would get with our regular rules. We could draw a resonance structure, moving these double bond electrons up to the oxygen, and our double-headed arrow. And then remember our formal charges, minus here and then plus on the oxygen. Excuse me, plus on the carbon. But now we have another problem, right? Carbon has a sextet. Carbon no longer has 8 electrons around it. So that's not good, right? So we would call this the major resonance contributor, and this is the minor. So we do observe a hybrid of these two structures, but what we see is closer to the major structure than the minor structure. So maintaining the highest amount of octets is one thing to keep in mind. Another thing is to keep formal charges as close to 0 as possible, or to have as few formal charges as possible is another way to put it. So if we draw the Lewis dot structure for formic acid, which is a different molecule related to formaldehyde, we come up with this structure. Like I said, if you need more review on drawing loose dot structures, feel free to see my previous video on bonding. We get this structure here, where we have now 2 oxygen atoms bonded to the carbon. What we could do is swing these electrons down to make a double bond, and then take these double bond electrons up to the oxygen. And then our formal charges, now we have minus here on this oxygen, and now plus on this oxygen. So again, this will be our major resonance structure because its formal charges are all 0, whereas this structure will be minor because charged atoms in any molecule are going to be a little bit higher in energy than neutral atoms. And usually we don't like to have the separation of charges like this. Remember that if you have a minus and a positive charge, they're going to want to attract each other and cancel out. So separating these charges is going to raise the energy of our system and make this a minor contributor. A third thing to keep in mind is if we are forced to have formal charges, keep them on atoms that like to have negative charges. Or, for example, if you have a positive formal charge, on a less electronegative atom. So let's say corresponding to electronegativity. So what do I mean by that? If we have this compound here, we have a formal charge of -1 on the oxygen, because it has 7, it owns 7 of its electrons. And all the other formal charges are 0. And what we could do is take one of these lone pairs, like we have been doing, and swing them down to make a double bond. And that's going to make a double bond between the carbon and the oxygen, so that's going to be more than an octet, which means we have to get rid of one of these double bonds here. Swing them over to the other carbon. So that's going to make a lone pair on this carbon. And now what formal charge do we have? Now our minus charge has moved to this carbon atom. And now we have a minus charge on an atom that is not very electronegative, which is going to be not favorable. Oxygen is more electronegative, so it prefers to have the negative charge close to it, or on the oxygen. Carbon is less electronegative, so it would rather have the neutral charge. So this will be our major structure. And with the negative charge on the oxygen, on the carbon will be our minor contributor. So that's going to be the end of my discussion on resonance. If you do need more practice, I will try to link some resources, because resonance is, like I said, a very important topic in organic chemistry, and we'll be discussing it more as the course goes on in relation to the actual chemistry going on. So the next thing I do want to talk about is molecular orbital theory, which is also very important to understand the behavior of a lot of organic molecules. So hopefully we know about atomic orbitals from general chemistry. From the periodic table, remember, we have s orbitals, which are shaped like spheres, p orbitals, which a lot of times are described as like dumbbells or figure eights, d and f orbitals. And these are, I'm not going to draw them here, they're a lot more complex. But for organic chemistry, for our purposes, we will be mostly focusing on s and p orbitals. Molecular orbitals are just like they sound, orbitals that are involved in molecules and not just single atoms on their own. So these are what form bonds. For example, if we take dihydrogen, hydrogen gas, very flammable, each hydrogen comes with one electron, and that electron is in an s orbital, if we just look at the periodic table. So we can imagine one s orbital from each hydrogen, and that little dot representing the nucleus. And we can imagine that these will form a molecular orbital. And one thing to remember is that orbitals have both positive and negative signs. So this is different from the charge of the orbital, or the charge of a molecule or an atom. But we'll say that these are both positive. That means the wave function is positive for these orbitals. So to show how that matters, if we take two positive things, because they're the same, they're going to add together. So if you imagine two spheres adding together, they're going to come closer. Keep our positives here. And then you form a full molecular orbital. And that's going to look something like this, where you have one H here, the nucleus, and the other here. And the charge of this entire molecular orbital will be, the sign of the wave function of this molecular orbital will be positive. And with that positive wave function that adds together, we call that the bonding orbital. What happens if we have the opposite signs on the wave function? So if we have a positive wave function and a negative wave function, those are going to cancel out. So what this is actually going to make is, if you imagine the plus wave function and the minus wave function will cancel out in the middle, what we actually end up getting is a separation. Down the middle here, we call that a node, where there's zero probability of finding the electrons. And because there's no electrons between the atoms, remember that from general chemistry, the square of the wave function is the probability of finding an electron at a particular place. It's the electron density. Because there's no electron density between the atoms, there's no bond, right? Can't have a bond if there are no electrons between. So we call that the antibonding orbital. Start a new page. One way we can represent these is with a molecular orbital diagram. So instead of drawing the orbitals out, which is relatively easy for s orbitals, right, because they're just spheres, but it can get quickly more complicated with anything more complex than that. So we can imagine we have two hydrogens here, and I will explain this in a second. We know that they each come with one electron in their neutral state. So we'll draw those electrons with a little arrow, this one pointing up, and this one pointing down. These lines represent where the energy is. So this is our ground state energy. We'll just say that that equals 0 relative to the other energies. This is going to be positive delta E. And this will be negative delta E. This is our change in energy when we move these two electrons into a molecular orbital and not an atomic orbital like they come. And remember that we're always looking for the lowest possible energy state. And so we want as much negative energy as possible, as much decrease in energy. So we're going to take these two electrons and put them in this molecular orbital here, because two electrons fit in one orbital from general chemistry. And that's going to be our bonding orbital. This orbital up here is antibonding. And because we have no electrons there, that's good. That means we have an overall decrease in energy, which is going to be favorable. And that's why you see H2 in nature. If it were not favorable to form, it would be incredibly rare, and we would probably have to manufacture it. So to demonstrate that, what if we take a hypothetical molecule of He2 helium? So helium is one of those noble gases, remember? It also has very simple electron configurations, so remember it's element number 2, so it's got 2 electrons in its ground state. And we can draw the same sort of diagram for helium. And we have 2 molecular orbitals, so the only way we can fill those is by putting all 4 of the electrons into these 2 orbitals. So that means our change in energy is going to be 0, because the positive delta E is exactly canceled out by the negative. And because there's no incentive to bonding, there's no negative delta E, then we don't see helium bonding with itself. We see it as a monatomic gas, just single atoms of helium. Hybrid molecular orbitals form in more complex structures. ones that involve more than just one s orbital bonding with another s orbital. And these are going to be most of the orbitals that we're interested in organic chemistry. So for example, if we have beryllium hydride, BeH2, that's going to have a couple hybrid molecular orbitals. So beryllium has one s orbital and one p orbital. We can see that from the periodic table. And these are just the orbitals that have electrons in them in the ground state. And we already know that hydrogen has one s orbital. So these are actually the beryllium orbitals are actually going to form a hybrid sp orbital. And we can see what that might look like is if we draw an s orbital here, and that's going to have a positive wave function. And then if we overlay a sort of p orbital, and p orbitals have a node in the middle where that kind of dumbbell crosses over. So it's going to be positive on one side and have a negative wave function on the other. And if we sort of add those together visually, we can think the positive s and the positive p orbital are going to add up on one side to make this p orbital really large, and they will cancel out on the other side to make it quite small. Minus and plus. So when we have two of those hybrid orbitals, because we have one p orbital with each sign of the wave function. So we have a p orbital that's positive on the left side and one p orbital that's positive on the right side. That's going to make our sp hybrid orbital. And then that can go ahead and bond with an H and an H. Where our beryllium is in the center here. And one thing to remember is that the number of atomic orbitals that go in has to equal the number of molecular orbitals that go out. So that's why when we have one s orbital and one p orbital, we come out with two sp orbitals, one pointing in each direction. We can represent those as bonds. So if we look at another molecule, BH3, boron has now one s orbital. It's filled. And now two p orbitals. And that's going to make, remember, we have one s orbital plus two p orbitals, so we're going to come out with three molecular orbitals. Three sp2 orbitals. And those are going to look just like the ones that we just drew, where we have the s and the p adding together. So I'm just going to draw the large lobe for each of these without the small one, where our boron is in the middle here. And then we have one H here, 1H down here, and 1H here, where each of those are using their s orbitals to bond. And remember, like we talked about in the previous video, these orbitals want to be as far away from each other as possible. So this is going to be 120 degrees. Forms a triangle. This is going to be 180, remember. And if you remember the last video, we also talked about another important bond angle in methane, CH4. Carbon has one s orbital, three p orbitals, that's going to make 4 sp3 orbitals. Remember, the number that comes in must come out. And that's going to be, if we have our carbon in the middle here, if you can imagine my bad drawing here, having a sort of tetrahedral shape, where this bond right here is coming out of the paper, and this bond is going into the paper, whereas the other two are in the plane of the paper. So it forms a tetrahedron, and these angles are 109.5 degrees. So one last thing to discuss are called sigma and pi bonds. Those are also very, very important in bonding and structure in organic chemistry. So a sigma orbital, a sigma bond. This is the Greek letter sigma. And these are when molecular orbitals are in the same plane. So for example, if we have a molecule of ethane, and I'll go over, remember, I'm giving a lot of these molecules as examples. I don't expect you to know what any of them do or how any of them are related to organic chemistry yet. I'm just using them as a lot of examples for a lot of these introductory concepts. We have a C-C bond in the middle, and I'm going to abbreviate all the hydrogens like so. And this C-C bond is going to have, remember, our sp3 orbital, where the carbons have this bond between them because of the overlap of their sp3 orbitals. And this is what we call a sigma bond, because these are in the same plane. They're pointing towards each other. Sigma bonds are also what we call single bonds. And they're the most common in bonding. We also have pi bonds. In Greek letter pi. Those are when the molecular orbitals are perpendicular to each other. Or excuse me, they'll actually be atomic orbitals. So I'll show you what I mean here. Perpendicular. If we have a molecule of ethylene, C2H4, in this case, each carbon is going to have an sp2 orbital. So carbon is special. It can hybridize a lot of different ways. So can other atoms, but that's why organic chemistry is based around carbon. It's very versatile in bonding. So these are our sp2 orbitals. And sp2 orbitals, remember, we're going to have the big p lobe here. And again, I'm abbreviating the hydrogens. But these are the sp2 orbitals. And if carbon hybridizes in sp2, like in an sp2 fashion, then it will have empty p orbitals above and below. So these are p orbitals. These are sp2 orbitals. So here, between the carbons is our sigma bond, because those hybrid orbitals are in the same plane. They're overlapping a lot. And our pi bond is actually the overlap of these empty p orbitals. Are not necessarily empty, because they do have electrons in them. That's what makes the double bond. But the p orbitals that are out of the plane of the sigma bond. So multiple pi bonds make double and triple bonds. So if we look at one step further, C2H2, which is acetylene, as a triple bond, if we draw the Lewis dot structure, and that's going to have multiple pi bonds. We can draw the sp2 orbitals again. Excuse me, sp orbitals. Remember that these are hybridized sp. But now, see if I can draw this here. We have one p orbital for each carbon that's pointing up and down, if we imagine that. And let's see if I can do this. Now we have another set of p orbitals that's pointing out of the paper and into the paper, so perpendicular to the plane. So let's draw these in different colors here. This is our sigma bond. Now we have two sets of pi bonds. This is our one pi bond. And let's do another red. The overlap of our second set of p orbitals gives us a second pi bond. So having two pi bonds gives us a triple bond. So it's intuitive to imagine that sigma bonds are stronger than pi bonds because sigma bonds they have much more overlap because they are in the same plane. However, whenever you have pi bonds, you are guaranteed to have sigma bonds. Sigma bonds are always, remember, those are single bonds, so they are going to form no matter what. So the total effect is stronger. So double and triple bonds are stronger than single bonds alone. So be careful to understand that. The pi bonds themselves are weaker than sigma bonds because they involve less overlap, more kind of a gray area of overlap. But if you are adding pi bonds to a sigma bond, like you do in a double or triple bond, they will be much stronger than single bonds. Okay, that wraps up my discussion on resonance and molecular orbitals. Thank you again for subscribing and looking into total organic chemistry, and feel free to check out my Patreon page that I will link in the description. And join me for the next video where I'll be discussing a little bit of thermodynamics and kinetics for another review session.